Okay, so this one is faster. Concurrent key value store with in-place updates from these people at Microsoft and the University of Washington. I forgot to put it in, but it's VLDB 2018. So with data-intensive applications and the sort of explosion in data, as we talk about a lot these days, we have a very specific set of challenges. So the first we can say is large state. What we mean by that is we need to access data that is perhaps much bigger than our main memory capacity. For example, some ad provider might have click-through rates for billions of users, which we might not be able to fit in memory. The second is that a lot of these workloads tend to be either update or read, modify, write intensive, as opposed to something like insert intensive workloads or read intensive. Maybe some examples are things like counters, lists, or monitors that update statistics for a device. The third is that even though we might have very large state with maybe billions of objects or key value pairs or whatever, typically only a small fraction will be active at one time. So for example, if we have a search engine that has statistics for billions of users, maybe only a few million are active at one time, and we can fit that amount of data in memory. Fourth is that in a lot of these workloads, range queries, maybe we don't need them so much, and hash tables are sufficient, so we don't need to do any work in the background or the foreground to keep things in order. Point operations are okay. And if we do need range queries, we can maybe serve them by other workarounds. And the fifth is that even if the workload fits in memory, we still need it to be ready for analytics later. So it needs to be made available offline and persistent for maybe someone else to process the data or something like that later. And if we take all of these challenges into account, we can think what the limitations are for sort of existing solutions. So one solution they talk about is partitioning the state and using in-memory only data structures. So for example, we could have a lot of state that we can't fit in the memory of one machine, but we partition it across maybe hundreds of machines, which can work, but it can be very expensive and can make recovery from failures either impossible or very complex. And in particular, we can really underutilize resources in a machine. So if we partition some large data set across hundreds of machines, each machine will typically have such a low request rate that the CPU might be really underutilized each time. Another solution we can look at is key value stores, which pretty much all the time suit data that's larger than memory, and most of the time have some sort of a settled failure recovery mechanism. But a lot of key value stores have different optimization targets than the ones we talked about previously. So they might just focus on blind updates, reads, and range. And more importantly, I think range scans. Range scans in particular just cause a lot of extra work in the background in general. And because of these limitations, these KV stores, even if the data fits in memory, they might not scale past a few million operations per second. So in this paper, they introduced faster, and the goal is that we have this store that is a combination of these targets that other systems might not provide all at the same time. So we want it to be highly concurrent, handle data that's larger than memory, but with very fast in-place and read, modify, write updates with little attention paid towards scans. And when we have very fast in-place updates, or we focus on in-place updates as well, recovery becomes less of a concern because we can overwrite data and lose it. And there are three components of the store in the paper. We have this threading model called epoch-based threading model. Just going to focus on the storage stuff for this paper. So the threading model is in the paper. We have the hash index in memory, and we have these an append only log and this novel log called the hybrid log for the storage. So if we could say maybe it has three key design points in this store, and it's fast concurrent record access, and our choice of when and how expensive operations are performed, like checkpointing and resizing, and most of the time allowing in-place updates instead of just appending everything to a log or copy and writing everything. So just as a quick overview of the architecture, And we have a lot of threads accessing a hash index. And inside the index, we have these pointers to records, which we can just say are almost like key value pairs. And then depending on what type of workload we have, we can either have totally in memory and append-only log, or this new hybrid log that they introduced. So if we look at the table on the bottom, all three allocators are concurrent and latch-free, but only the append-only log and hybrid log allow us data sets larger than memory. And only the hybrid log allows in-place updates. So the append-only is just normal. So for the hash index, we have this concurrent latch-free and resizable index. And won't focus so much on the resizing because it's just in the appendix of the paper, but what we have is a hash value for a key or something like that. And this value maps to a bucket, a hash bucket that's the size of a cache line, using what we call the first k bits. We call this the offset of the hash key. And then we say the remaining bits of h, the hash value are the tag. So one invariant or rule they follow in this index is that every offset and tag combination must have a unique entry in the index. So we can't have duplicates. And then, so a bucket is 64 bytes, and we have 7 entries in each bucket. And then this little entry at the end is pointer to an overflow bucket if we need it for later. And then the record format is just key value and then some metadata. So to search the index, in this diagram, we might have a bucket with ID 0. So we have this hash code for a key, and we take the first k bits, which maps to bucket 0 in this example. And then we have the remaining bits that are the tag. So what we do is very simply, we just search left to right for the tag. And once we find the tag, we have this record inside where we have what we call tentative bit, which I'll explain shortly. We have the tag just to match, and then we have the address, which could be in memory or on storage. Searches are simple, but the concurrent inserts are a little bit more involved. So a naive way we could concurrently insert is, for example, we have 2 threads, and they're both inserting something that has the tag G5. So we have this bucket here that has G1, G2, and then 2 empty slots, and then G4 to G8. And if we just wanted to naively compare and swap, what could happen is the first thread 1 compares and swaps slot 5, and then thread 2 will compare and swap slot 3, which will insert, the inserts will both work, but the problem is now we have 2 slots with this tag G5, and what they want to protect or enforce in this index is that we only have 1 entry per offset and tag combination. So this doesn't really work. So how they do it is they have this thing, they have their own version of a 2-phase insert. So when we have 2 threads inserting, like in the previous diagram, first each thread will set the tentative bit in the record. So it's just the first bit. And then next, each thread will rescan the bucket for duplicate entry. And if we find another entry with the tentative bit set, it means someone else was also trying to write the same thing. So if it's found, we back off and we retry the insert again, which might lead to 2 threads inserting at the same time and both failing, but it allows us to never reach a state where we have a duplicate entry in the index because of this sort of 2-phase insert. So when we want to handle data larger than memory, they introduced an append-only log in this paper, but it's just for the purpose of demonstration. It's not their main contribution. So just as an example, we have this. We define a logical address over disk and memory, and it starts on disk. So we have logical address 0, all the way into memory where we have this circular buffer. And in memory, we have this head offset and tail offset. So the head offset, we can say it gives us the lowest logical address available in memory, and just the same with the tail offset, or the opposite. It's the next free address at the tail of the log in memory. And when we want to allocate a new record, we just do it at the tail, and if we need to, we move the head offset if the log in memory is getting too big. So if the log in memory gets too big, or what we need to do is evict pages to storage. So we have these two bitmaps for the flush status and the close status of all the pages in the log. And when the tail moves in this append only allocator, the previous tail is flushed to storage. So then we change this flush status to F for that page. And then later, when we need to evict pages at the head, because the log is getting too big in memory, we have to check first if this page is flushed, and then we wait for all the threads to see the updated head, and then we can just evict it from memory. So in this append only log, pages are flushed to storage, just when the tail moves, like a usual append only log. But as they say in this paper, there are some issues with append only, even though it's used quite frequently. And it's simple, and it allows us to facilitate good recovery transactions, rollbacks, and stuff like that. But in the workloads they talk about in this paper, we don't really need much of that, or it's not of critical importance. So what if we could just update things in place? So with the append only log, every update, we need to create a new record and then copy and write the previous value, and then update the index, which can be very heavyweight depending on the operations per second you need in the workload. So what if we could just update things in place, avoiding the data copies and avoiding updating the index each time? So they introduced this thing they call the hybrid log, where now we have 3 regions. So first is the stable region on disk, and this is just records that have been flushed out of memory. Yeah, and then so we introduced this new thing called a read-only region in memory. And what happens is that, I'll explain next this mutable region, but when pages leave this mutable region, they enter this read-only region where they can't be updated anymore. And if we want to update a record in this region, we have to copy it back to the mutable region. So having a little read-only region like this gives us a couple of benefits. The first is that because we know the records in this region are read-only, we can be guaranteed they're safe to just flush and evict without any synchronization. So we don't need to do any extra work there. And it behaves as sort of a second chance cache in memory before we flush records to disk. So if it's very active, we can move it back to the mutable region. And just, yeah, so records that leave this region are just flushed to the disk. And then we have this mutable region for in-place updates. So records that are updated in place in this mutable region aren't flushed to disk immediately. So what we have here is just a region of memory that we can configure the size of, where the sort of hot set of data resides and can just be updated quickly right there in memory. And records that leave this mutable region will move to the read-only page. So in essence, it's quite a simple store. We just have this hash index and then the logs to form the store. So to evaluate it, they evaluate it with the index and the append only log, or there's an evaluation with the append only log later, but the default is the hybrid log, the thing they introduce. And in the evaluations, they size this in-place update region at 90% of the log in memory and the read-only region at 10. So they compare against in-memory indexes. We have this Intel TBB and Mastery, and they compare against RocksDB and Redis, but Redis is only mentioned once, so I won't show it here. And even though RocksDB is highly optimized for scans, the argument is that if someone's choosing a store that if we need to handle state that's larger than memory, stores like RocksDB are what people are going to choose anyway, because that's what's out there. So that's the argument when we compare against stores like this that optimize for scans. So first we can look at the in-memory performance, and we have these graphs. The top is sort of a multi-threaded YCSB test, and they call it YCSBA variance, but it's it's not really. It's the first is 100% read, modify, write. Second is 100% update. Third is 50-50, and then I think it's the fourth is 100% read or 100% update. I'm not sure, but in any case, faster sort of far outperforms the other trees and RocksDB as well. I mean, we can't even see RocksDB on the graph because it's compared to the other ones, it's so slow. But the point of these sort of graphs is that between faster, Intel, TBB, and Mastery, faster is the only one that actually handles data that can be larger than memory, yet it still far outperforms them on these tests. They don't actually talk about why in the paper, but my assumption is that because of this lack of synchronization at the index, makes the concurrent updates very efficient and free of contention. So if we look at the top graph, even though it's ZipF, which means there's a really high amount of locality in the workload, the other indexes can still perform pretty poorly, and that's due to the contention they have on records in their indexes. It's not as lock-free or as efficient as faster. So second thing we can look at is performance when it's larger than memory. And I think this slide is very telling of the store in general. So we have this 27 gigabyte data set, and we have either 50% 50-50 read update or 100% update. And if we look at the graph on the bottom, when the memory budget is low, so if it's a 27 gigabyte data set and the memory budget is 10, for example, or 5, at 50% update, 50% read, it's almost the same as RocksDB. The performance is almost the exact same. You know, even though the store is designed for dealing with workloads that are bigger than memory, it doesn't avoid the storage bottleneck of reads to the disk. So in the 50% update, 50% read workload, it's almost, you know, RocksDB is almost as good as it. But if we look at the 100% update workload, it's way faster than RocksDB, but stuff's just getting written to memory. So I'm not sure of the fairness of such a test, but in RocksDB, it's getting written to memory too, but it's being flushed and there's compactions in the background, stuff like that. But for the faster one, it's just getting written to memory and maybe flushed later if it reaches the read-only region. But really good update performance. And then the final thing we can look at is the performance of this append-only log versus the hybrid log. So we have this 50-50 read update workload. And even though the append-only log is just sequential writes in a, you know, logically increasing sequential writes, this hybrid log still performs way better. And the claim is that because we need to read and copy every update in the append-only log, as pretty characteristic of append-only logs in general, it just introduces so much overhead that even if we increase the threads or stuff like that, there's just too much contention at the tail, and these read, modify, writes and contention of updating the tail is just too high compared to the hybrid log, where we can just update things in place. We don't really need to make many changes to the index, or there's no contention on the end of the log or something, because we're just updating things where they are, so in place updates. So to conclude, we have these modern data intensive workloads where we need fast update performance, high concurrency, and larger than memory state. And we can find some other stores that are maybe optimized for some of these, but not all. So they introduced this store in this paper, Faster, where they have this very highly concurrent in memory index, and a storage design or the index works with storage to allow us to have, you know, larger than memory state. And at times it significantly outperforms the in-memory stores and always outperforms the persistent stores they test against. That's it. Thank you.